In continuing our analysis of phasors, let's take a look at problem 7.29 from the book. And in this particular circuit, we have a current source that is going to be a time-varying signal. We have a resistor and a capacitor. And let's say for this example that we are interested in the current that is actually passing through this capacitor. Following our phasor sort of problem-solving technique, step number one for this problem is going to be to transform all of these quantities into the phasor domain. Step two is going to be, once we've moved everything into the phasor domain, to apply our standard analysis techniques. So we will analyze the circuit. And then step three is, because in our analysis we will be doing all of our calculations in the phasor domain, we will need to transform back into the time domain to get our final quantity. So step three will be to transform back into the time domain. So in step number one, we are going to take all of the elements of our circuit and transform them into their phasor domain equivalents. If we recall our circuit in the time domain, this source becomes a phasor with 12e negative 60j degrees. So remember, the amplitude comes down to here, and the phase comes up into the exponent. We are ignoring the frequency at the moment, but we will use it in our determination of the other phasors. We now need to transform our resistor into its phasor domain, which is just R, so its value remains at 20. We now need to transform our capacitor into its phasor domain equivalent. And the result of this would be negative j over, and again the frequency is 2 pi times 10 to the 4 times c, which is 1 microfarad, so 1 times 10 to the negative 6. And the result that we get when we reference it in a Cartesian format is negative 15.915j. So if we were going to draw that out really quickly on a number line, if here is our real components and these are our imaginary components, our z of c would just be down here at the negative portion of the complex line. Now that we've done that, again, what we should do is replace all of our components with little boxes to help us indicate that they are now phasors and they are no longer our traditional resistors and capacitors, because we are now in the frequency domain. We can combine these elements as if we would resistors, so they're all impedances, and so these two objects are now considered in parallel. And so if we wanted, we could combine them to get a total impedance of the circuit, but that is not useful for this particular circuit because we want our current here through the capacitor. And as a final change, just for the sake of completeness, let's replace this with our phasor for our current supply. Coming back to our circuit, we have now converted all of our elements into their phasor domain equivalents, and we want to know the current that is flowing through the capacitor. If this was a traditional resistive circuit problem, then hopefully you would recognize this as a current divider. So I have a current source with two impedances in parallel. And so just in the same way, if this was resistors, we could treat this as a current divider. We can say that the current flowing through the capacitor is equal to the current coming from the current source over the impedances of the resistor and the impedances of the capacitor. And if this was, again, these were all resistors, and this is the standard current divider equation, we've simply just transformed it into our phasor domain equivalents. Now we can go ahead and replace our quantities in here with our different elements from the circuit. So IS is 12e to the negative 60 degrees j, which I just magically made appear over here through editing. And we can replace our impedances with 20 over negative 15.915J plus 20. And again, we run into the common issue again of this is in a polar system and this is in a rectilinear system. And so we can't, on this sheet right here, do the math directly. And so what we need to do is transform this rectilinear system into a polar system. Because we are doing multiplication of these two quantities, it is easier to do it in a polar setup. And so this point here on the bottom, the 20 negative 15.9, this vector right here actually transforms to be 25.55 e to the negative 38.5 degrees J. And so we can replace this denominator with a polar representation. And so I'm just going to erase it here and replace this with 25.55 e to the negative 38J. And again, we don't need to replace the numerator because we can just consider this, e to the 0 in terms of, well, it's already in a polar format. And then the final result of this calculation, once you punch everything in, is 9.38 e to the negative j, 21.48 degrees. And so what we'll see in the next step is how we take this quantity here and transform it back into the time domain. In the preceding problem, we found that the phasor for the current through the capacitor, so the phasor of this parameter right here flowing through the capacitor, was 9.38 times e to the j, 21.48 degrees. And so if we were to convert this back into the time domain, this would be a signal that's 9.38 cosine. And we need to return the frequency that we had before, which was 2 pi times 10 to the 4 t minus 21.48 degrees. So again, our amplitude comes down here, our phase comes down here, and we have just sort of saved and recalled the frequency. And again, this frequency comes from this source right here, what's driving the circuit. Now again, if we compare this current through the capacitor with our original source that was being driven by the current source, that was a 12 cosine. The frequency was the same, and then the phase was 60 degrees. And so we can see a couple changes, that the amplitude has been decreased. So we did have a 12 volt amplitude wave coming through. Now it's only 9.38, again, because that current gets split between the two components. And we also now have a change in phase. Again, if you recall that the capacitor, the phasor for the capacitor is negative J over WC, and it also has that electric field within the capacitor that does not want to change instantaneously. It affects the wave that is passing through the circuit. And so because the phase going through the capacitor is negative 21 versus negative 60 of the source, it's actually more positive. It's actually in front of the wave. So again, if we drew a diagram here, and if black was our source wave, so if this was I of S, then red would be our wave through the capacitor, and it would be a little bit smaller, but then again a little bit ahead of the driving source wave. So this is a summary of our AC solving technique. Again, we have a three-step process. You need to transform into the phasor domain and find all of your equivalent values there. You will analyze the circuit like you would anything else, any KCL, KVL, by inspection, superposition, any technique we've used, as long as you transform it into the phasor domain, will still work. And then finally, in the end, you want to transform back into the time domain so you can kind of make a little more rational sense of the circuit that you're observing.